What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, there can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds, that's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum-lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion-resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. Robotic arms, lasers, and 3D printers creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part, final assembly. Rockets are assembled step by step, the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust, while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions. Vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings, but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types. Lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material, stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact, old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning, the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term, a gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. Water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila! A new product appears, the packaging for your favorite smoothie or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper, or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. Hey bro! Today, we're diving headfirst into the wild world of money. Straight to the US Bureau of Engraving and Printing. That's the spot where real deal dollars are born. The ones that end up in people's pockets and keep the global economy humming. But listen, these aren't just some random pieces of paper with numbers slapped on them. Every bill is a legit masterpiece, packed with cutting-edge tech. We're about to uncover the secrets behind that one-of-a-kind paper, the mind-blowing microscopic details, and the top-tier security features that make the dollar untouchable. You ready? Let's roll. This is gonna be epic. First off, forget about regular paper. Dollars are printed on some next-level stuff made by Crane and Company. This isn't your basic white office paper. It's a cotton-linen blend with a unique texture that's totally different from the usual. That's why dollars have that crisp crinkle and last way longer. The material is 75% cotton and 25% linen, with tiny colored fibers woven in that you can only spot under a microscope. Plus, the paper is packed with watermarks and embedded security threads, making it nearly impossible to fake. This paper gets delivered in massive rolls, each one guarded like it's gold. And boom, that's step 1 in the battle against counterfeiters. Now we're stepping into the engraving department, the place where the magic happens and the main design for each bill is born. This is where artists, known as engravers, carve out the intricate designs and portraits by hand on metal plates with jaw-dropping precision. Take those iconic presidential portraits, like George Washington on the $1 bill or Benjamin Franklin on the $100 bill. They're painstakingly recreated from photographs. And those lines that look straight? They're actually made up of microscopic details. That's another layer of protection. No regular printers pulling that off. Feeling a little outclassed? Don't sweat it. This stuff is straight up genius. Next up, we're heading into the heart of the factory, where the real magic of printing goes down. Check out those massive printing machines using the intaglio technique. That's fancy talk for deep engraving. Here's how it works. The metal plates made by the engravers are coated with ink, and then the excess is wiped off, leaving the ink only in the engraved grooves. The paper is then pressed onto the plate under insane pressure, transferring the ink onto it. Thanks to intaglio printing, certain features on the bills, like the portraits, have a raised texture you can actually feel. How cool is that touchable detail? This process happens multiple times because dollars are printed in layers. First comes the black ink, then green, and finally, other security features are added. Every year, they crank out about 7 billion bills here, with 95% replacing old or worn-out cash. Oh, and the ink? It's so tough that even if you bury a dollar bill for 20 years, you'd still be able to recognize it. In today's world, where counterfeiters are getting slicker by the day, money has to level up with serious protection. For instance, there's microprinting, tiny text you can only see with a magnifying glass, added around portraits or borders of bills. It's so small and detailed, it's practically impossible to fake. Then there are those special security threads embedded in the paper. Under ultraviolet light, these threads glow in different colors depending on the bill's value. For example, $5 glow blue, while $100 shine pink. And let's not forget the $100 bill. It's loaded with high-tech features like 3D holograms that shift and change depending on the angle you look at them. How's that for next-level security? Next stop, the offset printing section. This is where those background images, like the green and golden hues you see on dollars, are added. It's the second line of defense. Intricate patterns and color gradients that are almost impossible to replicate with basic tools. Rolls of future cash spin on cylinders, feeding into the printing machine. Once the ink is applied, the rolls are cut into sheets of the perfect size. Fun fact, a dollar bill lasts on average 5 to 8 years before it's retired. On the back of the $1 bill, you've got the pyramid symbolizing strength and durability, while the all-seeing eye represents divine protection. Pretty wild, right? Let's keep this tour moving. Bro, now we're in the room where dollars get their names. This is where each bill gets its unique serial number, printed in either black or green ink. It's basically the ID code for every single banknote. The next step? Stamping the Federal Reserve Seal. These seals show which of the 12 Federal Reserve banks issued the note. This whole process happens on high-speed printing machines that churn out thousands of bills per minute. And get this, the printing conditions are no joke. The machines apply 80 tons of pressure, and the wax-based ink is literally baked into the paper under high heat. The ink is specially designed to resist wear and tear, even something as wild as going through the wash. Oh, and here's a crazy stat. The total value of all cash dollars in circulation is over 2 trillion. How's that for some money talk? Before dollars leave the factory, they go through some hardcore quality control. High-tech scanners check every single bill for defects. Blurry ink, damaged paper, or misaligned designs. If there's any mistake, the bill is pulled out of circulation immediately. The ones that pass, they're neatly packed into stacks of 100 bills. The final step is packing the money. These stacks are loaded into special containers and shipped off to Federal Reserve banks. From there, they make their way to commercial banks and eventually into people's hands. The whole transportation process is locked down tight, with heavy security. We're talking millions of dollars here after all. When a bill is declared too worn out, it gets destroyed. Don't get teary-eyed, bro. Let's check out how it happens. Worn-out banknotes are tossed into industrial shredders that chop them into tiny bits. According to the Federal Reserve, around 5 billion bills are shredded every year, mostly $1 and $5 notes, since they take the hardest beating from daily use. But shredded cash doesn't just get thrown away. The Federal Reserve is big on keeping things eco-friendly, so they find ways to repurpose the materials. Here's a funny story. One time in Texas, some clueless criminal broke into a Federal Reserve facility, thinking he'd hit the motherlode. Instead of stacks of cash, though, he walked off with a giant bag of shredded money. Thinking he'd scored big, he dragged his loot home. Spoiler alert, shredded cash is worth zilch. The guy got caught within a day. Tough luck for him, but at least we got a good laugh out of it. In some states, shredded bills are pressed into dense briquettes that are used as fuel for energy production. Pretty cool, right? This process replaces wood or coal, cutting down on environmental harm. In areas with the right tech, the shredded cash can even be turned into compost, since cotton linen paper is biodegradable. Yeah, money literally gets buried in the ground. A portion of the shredded banknotes is also repurposed into souvenirs. For example, they're packed into clear balls or boxes and sold to tourists at gift shops in the Bureau of Engraving and Printing. It's a unique way to hold a piece of money history in your hand. So, how about it, bro? Want to snag a chunk of chopped up cash for your shelf? Destroying large sums of cash is a whole other level of operation. When entire series of banknotes are pulled from circulation due to design updates or new security features, the disposal process gets even more intense. The old bills are transported in armored vehicles under strict surveillance, and every step of the destruction process is carefully documented to make sure not a single bill ends up in the wrong hands. This massive operation is actually cost-effective in the long run. For instance, according to the Federal Reserve, the cost of destroying a single bill is just 0.03 of a cent, thanks to automation. Every day, up to 200 tons of banknotes are shredded across the US. Even the machines used to destroy bills are guarded as tightly as the money still in circulation. It's a big deal, but hey, with that kind of precision, counterfeiters don't stand a chance. When it comes to durability, $1 bills last about 6.5 years on average, while $100 bills can stay in circulation for up to 22 years since they're handled less often. Not bad, bro, especially when you compare it to the lifespan of large denomination euro bills, which is only about 5 years. So, how do they decide when it's time to retire a bill? That's where the Federal Reserve's specialized machines come in. These machines assess the condition of banknotes and flag the ones too worn for circulation. But here's the kicker: the actual disposal doesn't happen at the same place as the printing. The Bureau of Engraving and Printing only destroys defective bills that pop up during production. For example, if the ink isn't applied evenly or the paper gets damaged, those bills are immediately shredded. Quality control on point, right? A few years back, a group of criminals in the US decided to rob an armored truck carrying cash. They planned the heist down to the last detail, but they picked the wrong moment to strike. Instead of shiny, fresh bills, the truck was hauling worn-out banknotes headed for destruction. The plan might have seemed genius at first, but the payoff? Practically worthless. Talk about a major flop. Then there's the classic case of the thief who tried to snatch some cash from a bank. In his rush to get out, he grabbed a bag full of bills, completely clueless that it was rigged with die packs. The second he stepped out of the bank, boom! The capsule exploded, covering both the cash and the crook in bright, unmistakable dye. Those bills became totally useless, and the mastermind left a literal trail of evidence straight to where the cops nabbed him. Honestly, I bet that trail wasn't just bright red or purple. There was probably a little brown in the mix too. Not that the press would mention that part. Two brothers, one factory, and a feud that forever changed their destinies. But how did Adidas rise to the pinnacle of global sports? In this video, we'll uncover the fascinating story of a brand that began by producing military clothing and shoes from old tires. From the era of Nazism to Olympic records, from corporate rivalries to fashion revolutions, discover how Adidas sneakers transformed from a family business into a global empire that reshaped the history of sports. The idea for the Dassler family's venture into shoemaking was inspired by the First World War. In 1920, during a family meeting, they decided to start making shoes. This marked the beginning of a story that would eventually change the face of global sports. In the small town of Herzogenaurach, the Dasslers crafted orthopedic shoes for training war-disabled athletes returning from the front, as well as comfortable slippers for everyday use. Adolf Dassler, a calm and diligent worker, came up with the idea of making the upper part of the shoes from surplus military uniforms, while using old car tires for the soles. His older brother, Rudolf, who was more outgoing and an excellent salesman, handled the business side of things. On July 1st, 1924, the two brothers officially founded their company, calling it the Dassler Brothers Shoe Factory. Things were clearly going well for the two German brothers. Just a year after founding their factory, Adolf came up with the idea to create the first soccer cleats with studs. The studs themselves were crafted by two blacksmith brothers named Zellin. This soccer model, along with gymnastic slippers, became the core products of the Dassler factory. 2 years later, Adolf and Rudolf rented an entire building for their growing operation and hired as many as 25 employees. They were soon producing 100 pairs of shoes a day and eventually bought the building outright. In 1928, the brothers, together with a certain Josef Weitzer, improved the design of the studded cleats and secured a patent from the German Patent Office. That same year, the Summer Olympics were held in Amsterdam, where several athletes competed wearing Dassler shoes. Fame came knocking on the brothers' door. In 1929, the Dassler brothers improved their products, particularly their soccer cleats. They focused on refining the design, enhancing the quality of the studs, and adapting their shoes for professional sports. During this time, their footwear gained widespread use among soccer players, boosting the factory's popularity. 2 years later, Germany was hit by an economic crisis. However, this did not affect the Dassler brothers' operations. On the contrary, they began construction on the Villa, a 3-story building. Over time, the villa served not only as a home for their families, but also as a place to discuss business matters. The brothers and their families lived together in this house, which was conveniently located next to their factory. This made it easier to manage production and grow their business. However, living under one roof also led to many challenges for the families. Despite sharing a home, tensions between the two households began to surface. The kitchen was shared, and meals were prepared for both families, but their tastes and preferences often diverged. Rumor had it that there was even a silent competition over whose dining table looked more lavish. Meanwhile, the villa became a symbol of the rapid growth and success of the Gebrüder Dassler, Dassler Brothers, factory. By this time, the brothers' footwear was already well known among athletes. In 1932, sprinter Arthur Jonath took 3rd place in the 100-meter race, wearing Dassler shoes, of course. Fame entered the Dassler household and firmly established itself there. In 1936, Jesse Owens, also sporting Dassler shoes, set 5 world records and won 4 gold medals. The brothers struck gold as well, with factory sales soaring to over 400,000 marks. Just 2 years later, they opened another factory in their hometown. The outbreak of World War II in 1939 marked a turning point for the brothers and their business. Most private enterprises were forced to adapt to meet wartime demands, and the Dassler factory was no exception. Instead of producing athletic footwear, the factory shifted to making shoes for German soldiers. There were also attempts to manufacture components for anti-tank rocket launchers, but the equipment proved inadequate for such a conversion. Both brothers were drafted into the military, although the younger brother, Adolf, was soon recalled to produce training shoes for soldiers. Both brothers were members of the National Socialist Party, which was a common occurrence in Germany at the time. Although there are suggestions that their membership was purely formal, it left a lasting impact on the subsequent reputation of their brands. In 1945, the town where the Dasslers lived fell under the American zone of occupation. Rudolf was sent to a prisoner of war camp, while Adolf stayed behind and began supplying hockey skates to the United States. Quite an unexpected career twist, wouldn't you say? Initially, the Americans intended to demolish the factory, but Adolf managed to convince them that it was solely producing footwear. In exchange for the skates, the factory received surplus US military supplies, including tents, baseball gloves, and similar items. By the end of the occupation in 1946, the factory was in a dire state. Rudolf eventually returned home, and the brothers resumed their original craft, making shoes from leftover military materials. The 47 employees hired at the time were paid not in cash, but in firewood, yarn, and other essential goods. The tough times ultimately drove a permanent wedge between the Dassler brothers. After their father's death, their relationship completely unraveled. The exact cause of their falling out remains unclear. Some speculate it was due to differing views on Nazism. Others suggest Rudolf harbored resentment, believing Adolf could have secured his release from captivity but chose not to. It's also possible they simply couldn't divide their inheritance amicably. While the precise reason is unknown, the rift grew so severe that they decided to split the business. This marked the end of their collaboration, but the beginning of two legendary brands. Adolf stayed at the family home, known as the Villa, which was conveniently located near his new factory, the foundation of what would become Adidas. Indeed, Adolf established Adidas based on the old factory. The brothers agreed not to use their company's original name and divided the facilities. Adolf's firm was initially called Adas before evolving into Adidas, with Adi from his first name and Das from their last name. The iconic three stripes became Adidas's symbol. He simply added an extra stripe to the old logo. Adolf actively collaborated with athletes, particularly soccer teams, which helped the brand quickly rise to prominence in the sports world. Meanwhile, Rudolf named his share of the business Ruda, combining parts of his first and last names. However, he later rebranded it as Puma, which remains a major brand to this day. If you'd like a video detailing the growth of Rudolf's factory, feel free to let me know in the comments. After patenting an updated logo and name, Adolf created the first soccer cleats with removable rubber studs. The following year, he improved the footwear for playing soccer in adverse conditions, such as on snow or frozen ground. In 1952, Adidas began producing other items in addition to footwear. Initially, these included sports bags, followed by tracksuits made in collaboration with the owner of a textile factory. That same year, runner Emil Zadopek won 3 gold medals at the Olympic Games wearing Adidas shoes, marking a new milestone in the brand's evolution. 2 years later, the German national soccer team, outfitted in Adidas gear, won the World Cup. It was a sensation. Adolf's company signed a series of partnership agreements, solidifying its position in the global market. By 1961, Adidas had fully streamlined the production and distribution of textiles. 2 years later, the brand began manufacturing soccer balls. Shortly thereafter, Adidas introduced the world's first footwear with a molded polyurethane sole. In 1975, Adolf Dassler, with a remarkable legacy behind him, was named an honorary member of the American Sporting Goods Association. 3 years later, the legendary German passed away, and Adidas came under the leadership of his widow, Käthe Dassler. 4 years after that, she also passed away, leaving the company to their son, Horst Dassler. Horst carried on his father's legacy with distinction, even implementing improvements and reforms in the production process. However, tragedy struck again. 6 years later, Horst passed away, and ownership of Adidas fell to his sisters. The Dassler sisters quickly realized they couldn't manage Adidas on their own, so they sold 80% of the company's shares to Bernard Tapie, the owner of the French soccer club Olympique de Marseille. Under his leadership, the company declined, and Bernard eventually sold the controlling stake to Robert Louis Dreyfus. Louis Dreyfus shifted production to China and several other countries in East Asia. The strategy of using low-cost labor paid off, and Adidas once again became a strong competitor in the sports goods market. The brand also established its own network of flagship stores, achieving unprecedented sales growth in 1996. The company's upward trajectory has continued ever since.